Today we are going to continue our study of right triangles. Specifically, we'll learn about Pythagorean triples and the reduced triangle principle. As a review, let's take another look at the Pythagorean theorem. That says in any right triangle that one leg squared plus the other leg squared equals the hypotenuse squared. The legs are often abbreviated as A and B, and the hypotenuse is also given the variable c. Then we can say that a squared plus b squared equals c squared. Just to choose numbers, just to go over this again, if the legs were 1 and 2, they don't have to be, but I'm just choosing that as an example. If the legs had length 1 and 2, then we would say that 1 squared plus 2 squared equals c squared, or 1 plus 4 is c squared, and then when we add 1 and 4, we get 5, and then when we take the square root of both sides, we get the square root of 5. I am going to introduce some new notation here, where we can write the sides, or the lengths of the sides of the right triangle, with the legs first, and then the hypotenuse. As long as the hypotenuse is last, the longest side, as long as that's written last, it doesn't really matter which leg comes first. Usually it's smallest to largest. So when you go to enter it in Moodle, you're going to have to enter it smallest to largest. But always, as far as when you're doing this on paper, as long as the hypotenuse is last, the longest side is last, you should be fine. Now, this 1, 2, root 5 is not a Pythagorean triple. A Pythagorean triple is a set of 3 whole numbers that work in the equation. Okay, I'm going to hop up here for an example. 3, 4, 5 is the smallest Pythagorean triple. So if I let 3 and 4 be the legs of a right triangle, then I know that 9 plus 16 equal 25, and then 5 is equal to c. So that's the smallest right triangle that you can make that has only whole numbers for sides. This triangle is 99.9% of the time represented on every standardized test that involves right triangles. So you will see this or some scaled version of it. Now this leads me into the reduced triangle principle a little bit.
Hilarious.
So if I use that notation where I write leg, hypotenuse, I can note this as a 3, 4, 5 right triangle. If I do the same with these sides from smallest to greatest, 6, 8, 10, I notice that each of those numbers has a factor of 2. If I factor that 2 out, 6 divided by 2 is 3, 8 divided by 2 is 4, and 10 divided by 2 is 5. So this is also a scaled version of a 3, 4, 5 right triangle, where 2 is the scalar and 3, 4, 5 is the family of right triangles. Here also, I can write the sides from smallest to largest, and I notice I can factor a 3 out. 9 divided by 3 is 3, 12 divided by 3 is 4, 15 divided by 3 is 5. So the scalar is 3. The family is a 3, 4, 5. The scalar does not need to be a whole number. This is the Pythagorean triple family. You can have a non-whole number or a non-integer number as your scalar. Take a look at this triangle here. Each of the sides is multiplied by the square root of 3. So if I factor out that square root of 3, I can see that this side would have a length of 3, this leg would have a length of 4, and the hypotenuse would then have a length of 5. So the scalar is not an integer, but this is a Pythagorean triple, and a 3, 4, 5 is the family. Now that's one of the 4 Pythagorean triples that you will be required to know. The other 3 are noted here. So we need to know 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. Those can also be enlarged or reduced. The scalar 3 applied to a 5, 12, 13 would result in a 15, 36, 39, because 3 times 5 is 15, 3 times 12 is 36, and 3 times 13 is 39. So 14, 48, and 50 also have a common factor. If we factor out the 2, we can see that it is just 2 times the 7, 24, 25 triangle. Similarly, if we factor out a 1/2, 1/2 times 8 is 4, 1/2 times 15 is 15 over 2, or 7.5, and then 1/2 times 17 is 17 halves, or 8 1/2. That's another member of the 8, 15, 17 family. There are an infinite number of families, but you only need to remember those first 4. Once again, they are 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. You are required to know those. So the reduced triangle principle allows us to use the Pythagorean theorem with a lot smaller numbers. For example, if I had a triangle whose lengths were 9 and 12, and I needed to know the length of the hypotenuse, I could immediately use the Pythagorean theorem and say that 9 squared plus 12 squared equals c squared. But then I'm going to get 36 and 144, and then I have to figure out the square root of that. By using the reduced triangle principle, you reduce the difficulty of the problem. And remember, we always want to use the most recent axioms, so you do want to do this reduced triangle principle. So instead, what I can do here is factor out that common factor of 3. 9 divided by 3 is 3, 12 divided by 3 is 4, and then c divided by 3 is going to be some other number. I'm going to call it x. So then I can take 3 squared plus 4 squared and figure out what x squared is. So then 9 plus 16 equals x squared, and I should bring this 3 along for the ride, because my end result is going to be 3 times whatever that number is. So 25 is x squared. That means 3 times 5. The actual number we want to finish off that triangle is 15. Let's get to work. Initially, the book separates the problems based on families. So let's try to do one from each family as an example. When I look at problem number 1C, I already know that it's going to be in the family of 3, 4, 5. When I look at the given information that a leg is 28 and the hypotenuse is 35, I can see that there is a common factor of 7 in each of those numbers. So if I factor the 7 out, I get 7 times 4 and 7 times 5. That would suggest that the missing leg is 7 times 3, or 21. Now let's write this up. The notation that I'd like you to use is to write the scalar, then the family, That's the missing side, so I'm going to underline it. So 7 times 3 implies the missing side is 21.